Hello, this is Sean Boston. Welcome to Engineering Statics, and we're going to continue our lecture series on internal forces of structural members. This is the second lecture, and we're going to refresh you on what we covered on the first one before we start. So we looked at a beam with a load on it, and we made the analogy to an Olympic weightlifter. And we know that when he lifts the weight, he's not only going to feel the weight acting at his hand, he's going to feel that force being distributed throughout his whole body. He's going to feel it in his wrists, his shoulder, his back, his hips, his knees, everything. And if we think about the phrase, lift with your knees, not with your back, then that gives us insight that it's not only one place that a force acts, it's distributed many places throughout a structural system. And when we think about this person, he has a muscular skeletal system that certain parts might not be able to support as big of a load as others. Like your legs might be able to support a bigger load than your back. And if the way you do things makes a difference. The types of structures you have in place make a difference. And if it's loaded incorrectly, you can damage your structure. And that's exactly the same thing that can happen in a beam. So when this force, this load is put on this beam, it doesn't just act at this point where it's touching, that causes forces to be distributed throughout the beam. And we want to look at the details of that. When we do, and when we get good at this, we can look at more complicated structures like a bridge and analyze each individual member in that structure and look at the internal forces and know where they're maximum and know how much they are. And that can inform us in how to make a design decision to accommodate for those internal forces correctly. The sneakiest part of what we did was down here. So when we look at this beam, in the past we've always considered the whole thing with our control volume. And we look at all the external forces acting on it. However, what we want to do now is similar but different. Since we're looking at internal forces, we're actually going to start the same way, but we're going to slice through our structure at some point that we want to consider the internal forces for. And once we do that, we can look at what kind of internal forces are acting at that position where we slice through. Ultimately, if our system is in equilibrium and we have some kind of force from this pin over on the left-hand side, we know that this chunk of material doesn't accelerate away. So it's actually along this edge, the material inside of our control volume is actually touching the material right where we cut it. And the material, the bonds of the atoms are actually holding that chunk of material in place. And so we know that if we have this upwards force here from the pin on the left-hand side, we must have something from the material holding it in place, and that's called the shear force. Now, these two forces acting alone would inspire a clockwise torque, but we know it does not do that because it's in equilibrium. So what happens is our material provides resistance to that. It provides an internal moment to counteract that clockwise action with a counterclockwise action. Other things we looked at here too, we introduced vocabulary words, and we also looked at the sign convention about which direction is positive when we're talking about shear and bending moments. This can be kind of tricky when you're first learning. Please take time to look into this and memorize some of these facts. So let's analyze a situation where we look at the internal forces. Let's use our newfound X-ray vision, as you would say, to look at the internal forces happening in here. So what we have here is a beam supported on each end by a rope. There's 100 newtons acting exactly in the center. The beam is 10 meters long. We know that the tension in each rope is 50 newtons. What we want to do is analyze the shear as a function of distance across the beam, and also bending moment as a function of distance across the beam. So how do we do this? So actually we're going to pick the left-hand side, and as we walk across, we're going to make free body diagrams at different positions, taking different chunks of this structure into account. And as we walk across, we know that specific things happen on the left side, exactly in the middle, and right here. We have ropes on the ends and a force acting in the middle. Those are specific boundaries that will inform us how to make some free body diagrams and analyze. So to do this, we're going to do 3 different free body diagrams with 3 different control volumes. The first one is going to be this orange chunk that is sliced before the halfway point from 0 to less than 5 meters across. The next one is going to be this green chunk right here that's exactly at the center point. And the last one is we're going to do a free body diagram for some place slicing after the midpoint but before the end there. So when we look at that chunk that's sliced before the midpoint, we know that it's in equilibrium, so there must be a few things happening here. Since we have an upwards force from the left side rope over here, we know that it's in equilibrium, so we must have our shear force must be downwards, preventing the system from accelerating upwards. Now, those 2 forces alone, once again, would cause a clockwise rotation. So, we know our internal structure must be preventing this clockwise rotation by providing a counterclockwise moment. So let's run the numbers here using a sum of forces in the y direction and sum of torques about the left-hand side here, and see what we can come up with to get a feel and exact details on what's happening here. So if I start with the left-hand side here and walk my way across, accounting for all forces on this system, I can get a full picture of my forces. Because this is an equilibrium, the net force is going to be 0, and the net torque is going to be 0. Okay, so let's walk our way across here. So 0 net force happens because I have 50 newtons upwards, but because of our convention for shear and moments, this is actually going to be a downward direction for our V is going to be the positive direction for forces. So we can go through and say this is actually upwards, but by our convention that's going to be a 50 negative newtons. Okay, and then we keep on going across. We eventually get to our shear force. That's downwards in the positive direction. So we get shear force is equal to 50 newtons here. And we know that this is a constant. So no matter where we are along the beam, we're always going to have a constant 50 newtons acting. So now let's go look at the bending moment that's happening here. We know we're in equilibrium, so the net moment on our system is going to be 0. And we're going to walk our way from the left side all the way over to the right side, accounting for all the moments, and we should account for everything that's happening. So if we start on the left-hand side, our 50 newtons from the rope is acting at the axis of rotation, so nothing happens there. Keep on going. We come to our moment, and by our definition of putting the top in compression, that's going to be a positive, so we're good there. And lastly, we look at our shear force, which is going to be, we said was 50, and it's going to be that force is acting at some distance x, we don't know, it's somewhere between 0 and before 5 meters. And because that causes the bottom of that beam, this shear force times this distance is going to cause the bottom beam compression. That's going to be a negative number here. We get a function for the bending moment of 50 positive x. So when we think about this function, it's linear, and so we know if we're at a 0 distance from the axis of rotation, we don't have any bending moment inside this system. But as we go over further and further, it increases more and more. The reason for this is that as we extend outwards, our shear force is getting further and further out there, thus producing more and more torque. And we need more and more internal moment to counteract that. So we're getting to the end of our video. In the future, the next video, we're going to produce these graphs that explore the internal forces all the way across and come up with a couple of summary items. Thank you.